The next design is design of bituminous pavement with cement treated base. So, we will do a design proof check here for an assumed cross section and for any given modulus value here. So, we will assume a pavement cross section with cement treated base and cement treated sub base. So, from bottom if you go, you have a subgrade layer. We will take the modulus of subgrade layer to be 75 megapascal. So, above a subgrade layer, we will have a cement treated sub base, and modulus of a cement treated sub base using an IRC specifications, we will take it as a 600 megapascal, and cement treated base course we will take a modulus to be 5000 megapascal. So, if you provide a cement treated base course, you need a crack relief layer. There can be two types of a crack relief layer. One is a granular crack relief layer or stress absorbent member interface, which is a bituminous mastic prepared using a modified binder, and the typical thickness will be about 25 millimeter. If you provide stress absorbent member interface, that is considered as a non-structural layer. Here we will use granular layer as a crack relief layer. So, the modulus value to be used for the granular layer is 450 megapascal. So, we will stick to the IRC specification here. So, above the crack relief layer, we will use one layer of bituminous concrete of modulus 3000 megapascal. So, these are the Poisson's ratio value recommended by IRC 37 for different layers. So, let us stick to the same Poisson's ratio value. So, these are the thickness assumed: base course of 40 millimeter thickness, crack relief layer of 100 millimeter thickness, cement treated base course of again 100 millimeter thickness, sub base course is 100 millimeter thickness, subgrade is of an infinite thickness, and whatever modulus you have here is an effective modulus. So, now if you do a proof checking for this cross section, with that is with a cement treated base and cement treated sub base, you need to check for rutting on the subgrade layer, you need to check for fatigue damage on a HMA layer, and you also need to check for a fatigue damage in a cement treated base layer. So, here again, if it is a cement treated base layer, can damage during construction process itself. So, damage that happens during construction and damage that happens due to repeated loading after opening it to traffic. So, these are the parameters which we need to check. So, we know that rutting on the subgrade layer is induced by vertical compressive strain at the top of a subgrade layer, and fatigue damage on a HMA layer is induced due to horizontal tensile strain at the bottom of a HMA layer. So, you need to compute these values. So, this is now typically a 5-layered structure with the top layer as a bituminous concrete layer. So, you have an elastic modulus of 3000 megapascal. Second layer is a granular crack relief layer that has a modulus of 450 megapascal. So, third layer is a cement treated base course with a modulus of 5000 megapascal. Fourth layer is a cement treated sub base course with a modulus of 600 megapascal, and fifth layer is a subgrade layer with the effective modulus of 75 megapascal. So, Poisson's ratio for a cement treated layers are considered to be 0.25, other layers are considered as 0.35. So, we will give the assumed thickness here for each layer, and this layer is subjected to a 20 kilonewton load with a tire pressure of 0.56. Though it is a cement treated base here, we are subjecting the loading on the top surface, which is a flexible here. So, I just considered the tire pressure to be 0.56 here. So, we will determine strain at 4 points, 2 at the interface of bituminous layer and a base layer, and 2 points at the top of a subgrade layer. So, at the bottom of a bituminous layer, 40 millimeter depth, at the radial distance of 0 and at the radial distance of 155 millimeter. So, at the top of a subgrade layer, it is 340, and at the radial distance of 0 and 155 millimeter. So, we will use a dual wheel load. When you submit it and compile it, this is the result you will get it. Now, for we will identify what is tensile strain that causes fatigue damage in a HMA layer. So, HMA layer corresponds to this 2 points, this 4 points. and it is a tensile strain, so it is positive here. Now tensile strain positive, which corresponds to epsilon T. So a maximum value from this number is considered as epsilon T. So which is 0.000115. So this is the strain that induces fatigue damage in the asphalt layer. Now the second interface which we used here, which is at the top of a subgrade layer, we find out what is the vertical compressive strain on this. So maximum of these number is epsilon V here, so which is 0.0004355. So we will use a 90% reliability equation here, and you can find out what is NR and NF. So if you find a 90% reliability equations based NR value using this strain at the top of a subgrade layer, you will see NR to be 24.4 MSA. So what does it mean here is, if the pavement subgrade before it fails in rutting, it can cater to a traffic of 24.4 MSA. So corresponding to the fatigue damage strain epsilon T, the NF value is computed to be 270 megapascal. So this are corresponding to 90% reliability functions. So the critical failure here is a rutting subgrade, but it will cater up to the traffic of 24.4 MSA. Now the next analysis is cement treated base layer damage analysis that happens during construction process. So during construction or during the stage of construction, the load is going to directly act upon a cement treated base here, and keep in mind that cement treated base is a rigid plate here. So we use a contact pressure of 800 kilopascal for the analysis. So the vehicle type that is going to act on the pavement is, it's just a loaded dumpers. So now the axial configurations of this dumpers will be critically a front axial with a single axial single wheel. You can consider it to be a 80 kilonewton weight, and rear axial is a tandem axial with typically 240 kilonewton weight. As per IASI guidelines, we consider tandem axial to be 2 repetitions of single axial. So that is 2 repetitions of 240 divided by 2 is 120 kilonewton. So 2 repetitions of single axial weighing 120 kilonewton. Now, so we are going to subject this axial on the cement treated base. So we have only subgrade layer, subbase layer and cement treated layer. So first layer is going to be a cement treated layer, second layer is subbase layer, and the third layer is subgrade layer. So Poisson's ratio of a cement treated layers are 0.25, granular or subbase layer is 0.35. So thickness is, this is what we have assumed, and we are subjecting it to the wheel load of 30 kilonewton. So this wheel load corresponds to an axial load of 120 kilonewton that we have seen. So 120 divided by 4 wheels, so that gives you 30 kilonewton each wheel load. So tire pressure, this being a rigid, we consider 800 megapascal. Now we will consider 2 analysis point, and exactly at the interface of a base and the subbase layer. So the depth is 100 millimeter, and we will consider a radial distance of 0, 1, and other is at 155 millimeter. So we are going to use a dual wheel here, so use a number 2 here, and once you give all this input, submit and run it, this is the result you will get it. So we will use a MEPDG expression for the computation of a damage here, and in this MEPDG expression, it is a stress dependent and not a strain dependent like previous rutting and HMA fatigue damage. So the tensile stress at the cement treated base layer is going to induce this damage here. So the tensile stress maximum at the base layer, that is maximum out of this 4 here, is going to induce a damage. So the value here is 1.473 megapascal. So this is sigma T value. So, now I am going to use the sigma t value to be this. Modulus of rupture, as per the equation, it is 28-day flexural strength of a cementitious bed, but this is during construction. So, we open it, if you open it to a traffic after 7 days of a initial curing, so the modulus of a rupture will be 70% of a 28-day flexural strength. So, if you take 70%, that is 0.7 of 1.4, you will get it to be nearest 1 megapascal. So, you can substitute a modulus of rupture to be 1 megapascal, and for the stress of 1.478 megapascal, you will get the number of repetitions of a load of 120 kilonewton to be this. So, it is less than 1. So, this is the maximum repetitions that 100 millimeter cement treated base course can withstand before it fails in fatigue damage. So, if you want to increase this number, generally it will be like nearing 70 repetitions of tandem axial. So, if it is a 70 repetitions of a standard axial, it will be 70 into 2, that is 140 repetitions of a single axial. Now, if you want to compute this exact stress value for the 140 repetitions of a damper axial, you can just substitute in this expression and find what is the sigma t value, and you find out the sigma t value to be 0.795 megapascal. So, if you want a cement treated base to take care of 70 repetitions of a damper vehicle, you need to restrict the stress at the cement treated base to 0.795 megapascal. So, for that what should be the thickness? So, you have to do it only by a trial. So, I have tried it for a base course of thickness 215 millimeter. So, other parameter remains the same. The thickness of a base course was increased to 215 millimeter. So, the depth exactly where we need stress and strain is at the interface, that is 215 millimeter. So, the for a 2 wheel load, when you submit and run the program, this will be the result, you get it. Now, sigma t value here you can see to be less than what we needed. So, for this specific sigma t value will cater to a traffic of 173 repetitions of 120 kilonewton load. So, you need a minimum base course thickness of 215 millimeter. The next analysis is a cumulative damage analysis due to a repeated traffic load repetitions. So, for this we need an axial load data, grouped axial load data. Let us use this axial load data to see how to do a cumulative damage analysis. So, now when you closely look into this axial load data, it has only 2 types of axial, means I have just considered only 2 types of axial for example here. It does not mean that the road will not have a tandem axial, or we will not consider a tandem axial for the computation of cumulative damage. We consider all type of axial here for the computations. So, you have a single axial load. You can see that the single axial loads are grouped at the interval of 10 kilonewton, and you have a number of repetitions or expected repetitions for each load group of a vehicle. So, you can also see the tandem axial loads are grouped at an interval of 20 kilonewton, and you have a number of repetitions of each load group given here. So, we will see how to use this data and calculate the cumulative damage of cement treated base. So, this is a data. I have just taken a middle value for the stress strain analysis in the grouped data. From this middle value, the number of repetitions of the single axial value is already given here. So, if this is a single axial dual wheel, if this is a total axial load, so since it is a dual wheel, it will have 4 wheels. So, divided by 4 will give you what is the total wheel load. So, for each of these wheel load, we are going to compute the stress using IIT PAVE software. So, this is again a 5-layered structure, because this is after completion of construction. So, it is considered as a 5-layered structure. The top is a BC layer, The second layer is a crack relief layer, third layer is cement treated base, fourth layer is cement treated sub base, and fifth layer is a subgrade layer, and the effect thickness of each layer is here. Now you see that we have considered the cement treated base of thickness 215 millimeter. This is after verification of a damage of a cement treated base that occurs during construction. Now we consider a wheel load first of 47.5 kilonewton for the tire pressure of 0.8, and we'll observe stresses and strains at two different points, that is at the base of a cement treated layer, that is where we need sigma t, base of a cement treated layer. So it is going to be 215 plus 100 plus 40, so it is going to be 355. So we will compute at a radial distance of 0 and at a radial distance of 155. Now when you see the stress value, this will be the critical stress at this location. Now when you compute the stress value at the bottom of a cement treated base for the wheel load of 45, you can see that the stress value will be 0.792. So each one is a one analysis here. You compute the value of sigma t. Now for a modulus of rupture value MRUP of 1.4, you can compute a stress ratio sigma t by modulus of rupture if you know the sigma t value, and this is the stress ratio value. Now substitute the stress ratio value here in this expression, you will get the NFI value. So number of repetitions for fatigue life computed for different load groups to be this. Now we compute this life consumed for each group by taking a ratio of number of repetitions of that particular axial group and particular load group, that is 70,000 divided by NF value, which is 3.76 E4, we get the total life consumed by this specific load group and this specific axial. So when you compute a fine life consumed for all load groups and you sum it up, so this will be the final total life consumed by single axial group. So we expect this summation to be less than 1. Now you can see a cumulative damage analysis for a tandem axial. So tandem axial, again it is the mid value of all the load given here, and this is the number of repetitions of a tandem axial. So we consider one tandem axial to be 2 times the single axial. So we multiply this by 2 to get the number of repetitions of a single axial. So this is a total tandem axial load of 400 kilonewton. Now if you need a wheel load, single wheel load divided by 8, because you have 8 wheels there, so you will get a single wheel load. Now for this specific single wheel load, if you use IIT PAPE software or Ken PAPE software, you can find out what is the stress at the base of a cement treated layer. So now you will get this to be the stress. Now knowing the modulus of rupture, you can compute the stress ratio, and using this equation you can calculate the NFI value, which is a fatigue life. Now taking the ratio of this fatigue life with N value, number of repetitions, you will get the total life consumed. Now sum this total life consumed for all the load groups, you will get the summation here. So the final life consumed considering all the load groups, that is single axial and tandem axial, comes out to be 52.39 in this case, but this is the total life consumed by the given cross section, but we want to restrict this number to be less than 1. So for restricting this number to be less than 1, now we need to increase the thickness of different layer and try and to reduce this to be less than 1. You can try with this thickness and check it out whether this total life consumed comes to be less than 1. If it comes to be less than 1, so whatever thickness we assumed here is good enough to prevent a cumulative damage of a cement treated base layer.